Welcome back everyone. My name is Sagar and we are back here with another video. So today is day 195 of our POTD series and today this question name is count lucky permutations and this is given a hard level question and we can consider it as a hard level question because the brute force approach that we will get is not going to get accepted. So first of all we will just read the statement. We are given an array of integers n elements and a non-weighted undirected graph of n nodes and m edges. So first of all, we are given these four inputs, n that is the length of our input array, and that will contain this. So this will contain some number of nodes, and after that we have m that is the length of this graph, and that graph contains all the edges. So in this input, you can see in this example 3 1 that means this is an undirected graph and unweighted graph. So that means 3 to 1 there is an edge, and that is undirected. So we can also say 1 to 3 there is an edge, and from 1 to 2 and 2 to 1. So this is not an adjacency list, and we have to make an adjacency list to iterate much efficiently. Okay, and this thing is now clear. And after that, the details of each edge in the graph is given to you in the form of list of list. Okay, that is the thing input, and our task is to find the number of lucky permutations of the given array. So first of all, if you don't know, let me just tell you what is a permutation. So suppose this is our example 1 2 3. So what is the permutation of this? So first of all, if this is the input, so we can say we can just if permutations means we have to just change the order of any number, any values, any two values. So first of all, this is 2 3, then 3 2. So this is the permutation. Okay, and after that we can just place here 2 and then 1 3. So 2 3 1, and after that 3 1 2 and 3 2 1. So there are total of 1 2 3 4 5 6 permutations of this input array. Okay, so we have to find the lucky permutations. But what is the lucky permutation? We know these are the six total of permutations, है ना? And at an array permutation is said to be lucky if for every node vi. So that particular permutation is said to be lucky if any node vi. So this is our vi. So that is one node from I should be greater than 1 and less than n minus 1. So suppose this is a wrong statement here, and I don't know why GFG don't care about the statement of their questions. So here what it is saying. So first of all, this is our length. So n is equal to 3 and n minus 1 will be equal to 2. So I should be less than 2. So that means I should be maximally 1 and 1 should be also lesser than 1. So that is not a condition. I think here they should write I should be greater than equal to 1 and less than equal to n minus 1, because that is the most logical thing here. And in the array, there is an edge between the nodes vi and vi plus 1. So what it is saying, let me just tell you. So suppose for this example, so suppose I am considering this array. So in this permutation, is this a lucky permutation or not? So in that, we have to say that there is an edge between every node and its next we can say next neighbor. So there should be every node. And what are the we can say edges? 3 1. So there is a node 1 and there is edge to 3, and there is also another edge to 2. So there are only two edges, and we have to say after that 1 to 2 we have edge. So this is okay, and after that 2 to 3 there should be also edge, but there is not an edge. So this is not a lucky permutation. And after that we will check for this. We will check for this array. So 1 to 3 there is an edge, okay, but 3 to 2 there is no edge. So this is not a lucky permutation. And after that we are checking for this. So 2 to 1, so that means this is vi, this is vi plus 1. So that is the thing they are saying here, that there should exist an edge between vi and vi plus 1 in every node. So from 2 to 1 there is an edge, and from 1 to 3 there is also an edge. So this is a lucky permutation. So we have to consider it count is equal to 1. And this is not a lucky permutation because 2 to 3 is an edge, but 2 to 3 is not an edge. Okay, so this is not a lucky permutation. And this is because 1 to 3 is an edge and 1 to 2 is also here is an edge. Okay, and this is also not a lucky permutation. So one here and one here, so total of two lucky permutations, and that is the output here. Okay, and just don't confuse yourself with this thing that 213 is 231 is equal in our undirected graph. They are not equal. Okay, and we have to consider all the permutations and then find the lucky ones. Okay, and what is the approach? So the first approach that is coming to your mind is brute force approach, that you have to count all the permutations and store it somewhere. And you can also see the constraints are not that much high, and value can be maximally 15. And time and space complexity are expected time and space complexity are much higher. So the first approach that may be coming to your mind is you can just generate all the permutations of some n length, and you will just store it somewhere. Okay, so you will create a list of lists and you will just create all the permutations here. You will just store all the permutations, but that is not a good approach, because the total number of permutation for length n is equal to n factorial, and you will just take time n factorial to generate all this, and also space to store all the permutations. And after that, you also have to check for every single permutation. You have to check, is there a valid, we can say, array or not, valid permutation or not. So you also have to traverse in that again, and you have to check for every array that it is a lucky permutation or not. So that is not going to be a good solution, but we just cannot do that because time complexity is much higher. And if you also watched our time and space complexity video, then you know this thing, that n factorial is worst time complexity that you can have. So you should always avoid it. And after that, so what is the second approach we can do? So I was also thinking about all this, but I just can't think of an approach that was coming. So I just watched some hints, and I was just practicing all this. So that is the thing. I just every time I can't just solve all the problems, so I also have to watch some hints and solutions. Okay, so let me just explain the solution here. So what approach we are going to use here is, so first of all, we have to check all the numbers, right? So first of all, we will just create an DP that will contain all the numbers. So first of all, there will be how many numbers of, we can say, how many numbers of total number of total number of permutations that we can have that are ending from some particular number. Okay, so we have to just store that thing. And I think what is the best explanation for this will be, let me just think of an approach. How can I explain to you? So first of all, we have to create a DP, and what is the reason? Because there will be repetitive cases, and that will be, so first of all, in our DP, at one index, what we will store, this will be I into 2 to the power n. And what is the reason for is I into 2 to the power n? I is the length of our total number n, and why it is 2 to the power n? So first of all, we are creating a DP of this length, integer array, not integer array, this will be long array, DP. And I will just explain why we are creating this length, n into 2 to the power n. So the better way to write 2 to the power n is 1 right shifted n times. And what is the reason why there is 2 to the power n? And that is because we have to store the total number of permutations that are ending with some particular number, and that are here 2 to the power n. And I think if you are not understanding it, let me just explain the complete approach, and I will just explain what is this. And suppose after that, first of all, we also have to create that adjacency list that we are talking about. So this is a graph, and we have to create first of all adjacency list. So I will create that, and that will be of length n into n, because there are total of n numbers. And after that, I will just traverse in this array. I should be less than m in this graph. So after that, adjacency of, and they are given on one base indexing. So you can see here, this is 1 2 3, and we will just change it to 0 base indexing. Okay, so on ith and 0th minus 1. So adjacency list will contain, we can either create it as boolean, or we can just we can just make it integer. So I will just make it a boolean, because there are only two values we can have. Either there is an edge between this I to this j, or there is not. So we will just say there is an edge, so it will be true. And graph of I 1 minus 1, and we have to just repeat the same thing. Here it will be 1, and here it will be 0. So that is how, so this is our A and this is B. So A to B, there is an edge, true. And after that, B to A, there is an edge, true. So that means 3 to 1 and 1 to 3. We are creating our adjacency list. Okay. And after that, what we have to do? First of all, let me just explain why we are creating here DP. So total number of 2 to the power n, and that is because uh, first of all, this what is the reason of creating this DP? So at every index, what we are storing, first of all, n, this is our I index and this is our j index. So I means, so this is our value. So there are three things here: a of ij. That means this is our value. So this is our value, and let me just write it here. So there will be three things: a of dp of I and j. So that means the value, total permutations, total number of permutations. So that is we only need total number of permutations and not the actual permutation. So this is 231, this is 213. So we don't need that. We need only number, permutation, total number of permutations that ends with I and contain all set bits of j. So what does that mean? I think you don't understand it. So let me just explain. So what is I here? So I represent the node. Okay. So I simply represent node. So that is the node that we are ending with. So first of all, let me just explain it. And uh, j will represent our visited array. So suppose we are not just passing here visited array. We are just passing j visited array like. They will represent like our visited array. So what is this? So first of all, there is some permutation 1, 2, 3. So this is our permutation and it contain all the three numbers, right? So what we will say, a of ij, that means dp of ij will be equal to 3 because there are total of three permutations. No, there are no total of three permutations. There are total of two permutations. 2, 1, 3. Yeah, this is there are total of two permutations that end with 3. Okay, and total of two permutations. So it will be equal to 2, and I will be equal to 3, and j will be equal to. So what is the value of j? In binary form, we have to create an array. So for a number, we can just create a binary form and we can consider it as an array. So j will be equal to, that will be, for a 32-bit number, it will contain 1, 2, 3. So that means at last 3 bits will be 1, 1, 1, and all the rest of the bits will be 0, 0, 0. So I hope now you understand it. This will be acting as our visited array. Okay, and that is the reason for creating this 2 to the power n array, 2 to the power n length, because the maximum value of j will be equal to 2 to the power n, and that is the total number of n we can have, and that is the total number of combinations we can make with these numbers. So suppose this is our, we don't have this 2 here. So if we don't have this 2, we will just remove this, and that means there are total of two permutations that have, that are okay. No, there are no two permutations. I think I have to write here 4 and 4 here. Okay, so there are now total of two permutations that are ending with 3. So I will be equal to 3 and j will be equal to, so j, value of j will be changing now, and the value of j will be equal to, all the values will be 0, and at last we will have 1 is visited. So first bit is set, and then third bit is visited. So 0. So the second bit is not visited, and third bit is set because 3 is visited, and after that 4 is also visited. So 1 and 0. I hope now you understand it. That means our first bit is visited. So what we will do, I right shift, 1 right shift I time. So if I is equal to 0, then 1 right shift 0 times. So we will just set this bit, and 2 is not visited in this permutations. Okay, so that is why we are storing this. They will have repetitive cases, and after that, whenever we hit 2, so we will just make permutations according to these numbers. So there are a total of 2 permutations that are ending with 3, and we can just make more permutations when we have 2. Okay, so that is the reason for creating this dp. And after that, what is the base case? So first of all, we have to fill some values in our dp array, and the base case will be, so a of ij will be equal to 1 and y1, because for some number I, when we have 1 here, and 1 means there is only one permutation of this number. So there is one permutation that is ending with our 1, and the j will be equal to, first of all, here I have to write I is equal to 1, and j will be equal to, all the values are 0, 0, 0, and at last this will be 1, and for I is equal to 2, j will be equal to, 0, 0, 0, 1, 0, and the same for all the values. For I is equal to 3, j will be equal to 0, 0, 0, all the values are 0, and then 1, 0, 0, because this is the third bit, and I is equal to 3 here. Okay, so that means 1 right shift I times. Okay, and this is I index. So that is the thing we have to store here, equal to 1. So for dp value I, so that means from 0 to all n, we have to say 1 right shift I times, so that means all 0 to n times, we have to say all the values will be equal to 1. So that means when there is only one array, one element that ends with 1 equal to 1 permutation, okay? And when there is our second, so there is only one node that end with 2, and there is only three node, third node that end with 3, and that only contains 3. So I hope now you understand this, and let me just write I equal to 0, I should be less than, so it will be n, and we have to write here dp of I, right shift, one right shift I times, because one right shift one time, so it will be 0 0 0 1, and one right shift two times, so 0 0 1 0, then 0 1 0 0, and all the bits are 0 here, 1 0 0 0. So that is the thing. So that means 1 is only visited, 2 is only visited, 3 is only visited, and 4 is only visited when we are talking about these arrays. So they are of length 1. That is why it is equal to 1 here, okay? And after that we have to use the same, this is called as bit masking. We are storing this as our visited array, and that is here bit mask. So this is our bit mask, and we will just say that this number is now visited, 1 is visited, and here 2 is visited, and here 3. So we have to just do the same thing, and after that we have to start our another loop that will say all the permutation, that will call all the permutations. So first of all, now we are talking about one numbers, and we have to now select two length, okay? So 1 2, so what is the total permutations of this 1 2? So that will be equal to total number of permutations of 1 and 2. So we have to just consider that, and for that I will just start with this bit masking. So it will be equal to 1. So what are the total number of bit masks that we can have? So first bit mask will be 1, then it will be 1 0, then 1 0 0, then up to how many number of n we have? So 1 0 0 0 0, okay? And I will just do the same thing. Our this is not I will just say it bit mask. So bit mask should be less than one right shift n times. So there, this is the same thing. So this will be our bit mask last value, one right shift n times. And every time what we will say, bit mask. Okay, yeah, we have to just write here plus plus. I think so. This will be first 1, and this will increase. So it will be 1 0, then 1 1 1 0 0. Okay, yeah. So first of all, it will be 1, and after that it will be 2. So first of all, it will be 1, and after that bit mask will be 2. That means we are only 1 means that we have only 1 as visited, and this means we have only 2 as visited, and after that it will be 3 1 1. So that means we will have 1 and 2 both as visited in our any permutation, and after that we will count the number of permutations. And after that, this after the 3 we will have 4. So 4 means 1 0 0. So that means only our 3 is visited. So in binary form we can see this is our third, this is our second, this is our first bit, okay? And so I hope now you understand it. What is the use of this bit mask? So it is here value of bit mask is equal to 4, but you can see the number of bits we can say is only 3 is visited. So that means there is an permutation that have only 3, that is ending with 3, okay? And that only contains 3, but we cannot say that it is ending with 3. So this means that there is a permutation that also contains 3 as visited. So that permutations contain 3, and after that it will be 5. So 5 means 1 0 1. So this is the value of our bit mask, but that means that this is our third bit. So 3 is visited, and this is our first bit. So 1 is also contains in our this permutation. So it can be 1 3, it can be also 1 3, it can be also 3 1. So there are total of two numbers, okay, that have 1 and 3, and the number of permutations that contains, so let me just clear this thing. The number of permutations that end with 1 and that contains 1 and 3. So the number of permutations are equal to only 1. So that is the thing, because the number of permutations that end with 1 equal to this one, and that also contains 3 will be this one. So 3 and 1, okay? And I hope now you understand this thing, why we are writing it as this. And after that, this is our base case. And after that, now we have to check for all the numbers from 1 to less than equal to n. Okay, we just had here zero base indexing, so we will write here for zero base indexing, and every time I will plus plus. So first of all, we will just check for 1, and 1 for 1, that means we are checking for the number that are ending with 1 and with this bit mask. So the number that are ending with 1 and only contains 1. and after that the number that are ending with 1 but contains only 2, but so the number will be obviously 0, because there can be no permutation that is ending with 1 and that contains only 2. So after that we also have to start another loop, and that is for our second number that we are gonna take. So this I contains our first number and this j will represent our second number. So it will be equal to, it will be also a number, so it will also start from 0 to n. And after that what we have to do, first of all we have to now make the value of this, we have to now change the value of this I, that this will be our first number and this is our second number. So what is the total number of permutations, and that will be equal to I. And okay, now we have to check are these the different number or not. So first of all, initially I and j are both 0, so we also have to check that if I is not equal to j, and also there should be a, first of all, between 1 and 3 there should be an edge. Okay, so first of all now we have to check in our adjacency list that from I to j. So from I to j there should be a, we can say, edge. So that means so from I to j there should be an edge, and I, okay, we have to contain, we have to check for this ith value, and this will be 1 and 2. So first of all we are creating, we are checking for any permutation and we have to check it on this array. So we will just get the value from this array, and that is also 1 base indexing, so we will just minus 1 here because that will be now 0 base indexing. So that means in our adjacency list, this value and this value, so 1 and 2 have a edge or not. So if they have an edge, and after that we also have to check the values in this array are not repetitive. So you can see in this example, in our second example, they have the same value. So we also have to check this thing that the values should not be same, and we also have to check that ith value is not equal to jth value. And after that we also have to check one more condition, and that will be equal to that this is a valid bit mask. So valid bit mask means that this value was previously not added. So that means 1 and our bit mask right shift j times is greater than 0. So what does that mean? I hope if you don't understand this bit mask thing, let me just tell you. 1 and bit mask right shift j times. So we have some bit mask 100, and we are right shifting it j times. So right shifting it j times means we are incrementing it like this. So this is our bit mask and we are left shifting it. So sorry, this is our left shift operator, है ना? And after left shifting we will have some values like this. And if this is our valid bit mask, that means when we are using it and operator with 1, so that means this will contain all the zeros here, so 0 0 0. And if this value is in our integer range, so it will be not here 0 and it will be here 1. And if this value is valid, then it should be greater than 0, and if it is negative value, then this will just pass our integer range. So if this is a valid bit mask, so that means here this is here 1, and so this is our bitwise AND operator, and this is here, okay, I think I just write here this thing wrong operator. So this is our left shift operator, right? We have to left shift this value, okay, and it is greater than 0, then we can just say this is a valid bit mask, and after that now we can do our thing. And the thing is, we have to update the ith value with this bit mask. So what will be the value? So that means this value, first of all, what this value will represent, that all the permutation, number of permutations that are ending with I and have all the visited value as this bit mask. So they will contain also the values that are ending with j. So now we have to increment it. Suppose this was representing 1. I is 1. So that means all the permutations that are ending with 1 here, and bit mask will be, suppose bit mask will be 0 1 0 0 0. So there are total of only one number of permutations that are ending with. So this will be equal to 1 first, and because I is equal to 1, so total number of permutations that are ending with 1 and have bit mass equal to this. So bit mass is equal to 1. Okay. So this is the thing. So it will be obviously equal to 1. So that is our base case. When bit mass equal to 1, I is equal to 0. So when I is equal to 0, we are checking for 1, and 1 as our element. And after that, that means this will be equal to, so we will just add some value. So it was initially 1, and what we have to add, so we will just add the value of this j. So what is the value of the j? So it cannot be 0, it will be 1. So that means we will check this 2. So what we will add, we will just add the value of this J. So the all the permutations that are ending with J. So what are all the permutations that are currently ending with J, and that contains this bit mask, but they should not contain this one. So if we are also saying 2 1, so suppose for our future permutations, this will have 2 1, 2 1 2, not 2 1 2, 2 1 3, and 2 3 1. So suppose for this permutation, so only we have to consider that one permutation which don't have this one. So that is why we have to use here XOR operator. So XOR means this will just eliminate this one if it is in, if it is not in this permutation, and if this one is in this permutation, so we will not consider this. So we will just not consider all the permutation that have this one. So that is why we have to use here bit mask with one left shift I times. So I know this question is little bit tricky, and this thing is little tricky, and also I think all the things are clear. This is our base case, and the main thing is this. So we have to only check for those permutations that only have other numbers and not the current number, or not the ith number, and all the permutations with J. So that is why we are using here XOR operator. And that is it. That is our base case. And after that, what we have to check? So we have all the numbers. So we have some three number of permutations that are ending with one, two number of permutations. Just for example, two number of permutations that are ending with two, and four number of permutations that are ending with three. So we have all the permutations. So we have number of permutations. This is the number of permutations that are ending with one, and that contains all the numbers, because we will just check for our last index of our array. So on our last index of array, we will just have all the numbers as visited. So what is the last index? We will just use here J. So J value contains bit mask, and what is the maximum value of bit mask when all numbers are visited? So 1 1 1 1. So bit mask will be equal to this. That means all the numbers are visited, है ना? And we have to just check for this one. That is our last index, and that will be equal to, so this value is equal to 2 to the power n minus 1. And I hope now you know this. If 2 to the power n will be equal to 1, 0 0 0 0 0, and if we minus 1 this thing, then it will be equal to 1 1 1 1. And we just have to check for this thing, that when all the values are visited. So when all the values are visited, and the one that is ending with 1. So when all the values are visited and the permutations that are ending with 1 equal to 3, and all the values are visited and the permutation is ending with 2. So we have to just check all the counts. And what we have to do now, we will just create our answer, long answer, and that will be starting from 0 4. We have to just check for our last row in our DP array. So first of all, we will check for all the I, answer plus equal to DP of all the I values. And so first of all, we will check for one, all the numbers that are ending with 1, and that contains all the permutations. So for permutation, we were maintaining this bit mask. And what is the maximum value of bit mask? The maximum value of bit mask is this, and that is here 2 to the power n minus 1. I just told this thing. So 2 to the power n minus 1 can be, we can just simply write it as 1 right shift n times minus 1. So 1 right shift n time is obviously 2 to the power n. You can just calculate it. And that is it about today, and we'll just return answer. So that is the final answer. We will just add all these values. So all the permutation ending with 1, all the permutation ending with 2, all the permutation ending with 3. And we are also maintaining the case that there should be an edge between them. Okay. So this is the condition that we have to write, and that is the main condition that we have to check. Okay. So what was the compilation error? Okay. ARR of, okay, that is 1, and I think we are missing some brackets here. No, we are not. So what is the problem? 1 right shift 1 and bit mask left shift j times. This should be greater than 0. I think okay. We have to make a bracket here. And the second one is there is only one error. I minus 1 and j minus 1 equal to 1. So boolean and integer. So this is an incompatible type. I is not equal to 0, and this value is equal to 1. And after that, this condition. So I think it is okay. There should not be a problem here. Okay, let me just check for the issue. There is an extra braces here. And that is the same error, boolean and integer. What is wrong here? What is the boolean value here? This is your ith value minus 1. And okay, this is our adjacency is ith value minus 1, and this is our jth value minus 1. And if that is equal to, okay, we are creating here this thing. We are creating a boolean value here. That will be true. Okay, we are creating a adjacency as boolean array. And if we were creating it as integer array, then you can just write it as equal to 1. And I think now this is our complete algorithm, and the time and space complexity you can just calculate it. Bit mask array is starting from 0 and starting from 1 and going up to 1 less than 1 right shift n time. So that is equal to, you know, this thing 2 to the power n. So it is here 2 to the power n, and inside this you can see n square. So it is here time complexity is 2 to the power n into n square, and the space complexity is, you can see we are creating a TP array that is of size n into 2 to the power n. So that is it for today, everyone. If you don't understand this approach, then you just have to practice this thing without bitmask. And instead of bitmask, just consider it as our boolean visited array. So you will just understand the thing if you are considering this bitmask as our boolean visited array. And you just have to one time just try run this thing, and you will just get used to it. So that is it about today, and you will just get this solution in our DSA repository. So thank you for watching.